go through an example, a tutorial on how to do the linear least squares fit or the linear regression graph. I'm going to make sure we hit every single one of these criteria points because that's how you're going to be graded. All right. I am not a huge fan of linear regression in general because not everything in the real world is going to follow a linear relationship. All right. We know that just by looking at the errors that are associated with the universe. But for the purpose of this class, we kind of have to do this assignment. Unfortunately, I have to assign you this work. And so if we're going to do it, might as well do a good job of it. And so I'm going to basically do a tutorial, a walkthrough on each of these points, and we're going to use this data here. All right. So I'm going to flip over to my whiteboard, and we're going to get started. So the first thing we want to do is we want to make sure we got this bad boy written out, right? For the title, I just don't want to see title, guys. I want come up with something. It doesn't need to be unique, but since our data is basically height versus time, that's what I'm going to write. I'm going to write height versus time. Pretty simple, right? Next thing we do is we're going to label our axes with the correct units. On a horizontal axis, that's going to be time. We're going to put that in seconds. If you want to write out seconds completely so it's really clear, you're more than welcome to do that. But if you just put seconds, that's completely fine with me. All right. If you're uncertain about where those units come from, all you have to do is go back into the data set and look at the units they use. If they use seconds and we're measuring time, use seconds. If we're measuring force and it's in newtons, use newtons. All right. Just follow the data set, right? So here we have height that is measured in meters, right? So for the first data set, the first data points, first column, I should say, we go up to 5. So that's 1, 2, 3, 4, 5. That's a lot of white space, but I'm new to this sort of writing notes online, so bear with me. The second column is going to be 2 to 6, so that's 1, 2, 3, 4, 5, 6. And what I like doing, right, you'll see as you get more practice with this, the linear regression is essentially, you're basically drawing a graph based on the data points that's true and most accurate to that data set, right? But I still want to see your original data points because the idea is, hey, your data set is pretty accurate, and if we eyeball it, we might get something decently close to the actual line. But if we use a linear regression, it's going to be the perfect fit for that line, all right, as perfect as you can get. I would recommend maybe when you graph these, you can use a star. I think a star would be fine. So let's say 1, 2 is our first data point. We draw a star there, 2 to 3, another star, 3, 4, another star, 5, 6, or 4, 5, another star, and then 5, 6. Boom. All right, and again, we can eyeball that and be like, cool, that's our line. But we want to be really, really precise with this because we want to minimize our error, right? So that's the next step. After that, what we want to do is use a sort of calculator, an online linear regression calculator. If you have an actual like TI-83, like a Texas Instruments calculator, or any sort of computational calculator that can do this, and you want to do the graph by hand, and then upload it as a PDF, you're more than welcome to. And in the next demo video, I'll kind of talk about what that submission guideline looks like. I'm kind of playing it by ear, but whichever works for you for the time being, we'll just go with that. All right. For me, since I'm doing online notes, I'm going to hop over to this quick linear regression calculator. This is the first thing that showed up on Google, and I have my values input in the X values and the Y values. And if you look, this looks exactly like the lines I just graphed, right? So I plug all these values in, and I get this. It should be no surprise that this is our equation. Y equals 1x plus 1. And why is that? The way I created this data set, it's basically a slope of 1, right? Perfectly for every set. And we start at 1, and that's why that's our y-intercept. So the next thing you write on this graph is going to be just that. I'm a fan of doing it this way. I always like writing y equals ax plus b, because that is just an indication that, cool, the next thing I'm showing you is this equation of a line. Some people prefer doing it this way. You can do directly 1x plus 1, or instead you can do from here, right? Obviously, write this directly underneath this, so I know what you're talking about. A equals 1, B equals 1, right? And so you want to pick a calculator that uses that gives you your correlation coefficient. This doesn't give me one, but since this is a perfect fit, right, I reckon that this is probably going to be 1 for R, right? Please make sure you check on that when you do this data yourself, right? But I would say that's a pretty good guess. So let's go back from the top. We have our title, we have our axes labeled, we have our points, all right, from the original graph. Then we have our linear regression. The last thing we need to do is basically plug points into this equation to get the points that fall on the line, which is this, right? So what I mean by test points is, I don't know, use two simple points like x equals 0, so y equals this. You're creating a coordinate or a point on this line, so you can connect those two lines, and that gives you the linear regression, if that makes sense. So let's say when x equals 0, we're going to plug 0 into that equation, right? And so y equals 1. Our new coordinate is 0, 1. So 0 is here, 1 is here. And that makes sense, right? What about when 1, we already used 1, so let's use like x equals 1.5. And you can be creative with these. I don't care, as long as you show your work for it, okay? So we have 1 times 1.5 plus 1, that's 2.5, right? So now our coordinate is now 1.5, 2.5. So 1.5 got there, 2.5 somewhere there, right? The last step, boom, connect those two dots, right? We just get lucky on this one, right? Because I chose these points to where our original data points are going to fall within that line anyways. That's not always going to be the case, right? You might get a situation where, let's say, your original points are somewhat scattered, right? And you find that once you line these up, those original points don't fall on that line, and that's completely fine. I actually prefer to see this because that lets me know that, hey, we had some sort of error associated with our experiment, and when we remedied that by doing the linear regression, we got a way better fit, right? Again, this class is a proof of concept, so we want to kind of prove things that are obvious. So we hit this title, our axes with the correct units, original data points, our equation, and test points. That was pretty quick, and once you guys get practice with it, it's going to go even faster, all right? But you need all of these to get full points for this graph, right? And typically, out of those 10 points assigned, it's basically going to be 1 full point, which is the graph, right? Sometimes we do graphs that aren't linear regression, but for the most part, like 99.9% of the time in this class we do a graph, it's going to be a linear regression. So make sure you follow that, all right? Cool.